Hi, Ms. Smith here with Enrichology Tutoring, bringing you a quick video over the concept of rational functions. So over here, I have this function graphed, and I'll go into how I got said function in a moment. And when I graph it, the behavior is largely determined by what we call the asymptotes. And there are two asymptotes here, a vertical and a horizontal. And we'll go about showing how I got said asymptotes and what that means for the behavior of the graph. So we have our word problem here. I like to use word problems to help give context, real world context into the math. So in this word problem, we have a small drone, and the function is talking about its flight time, which we can determine if we have the total payload weight or whatever cargo it's carrying. If we have its weight and plug it in for the value of x, we can find how long or what will its time of flight be. So with this function, this is a rational function. We have a polynomial in the numerator and a polynomial in the denominator. A polynomial, of course, applies to these rules. We have some constant integer or real number up here, and we have x raised to some non-negative integer. So whenever we have that same basic thing, we have a polynomial. Over here, when I originally graphed it in Desmos, I just put 120 divided by x minus 1. This is the same as saying 120 times x to the 0th power. Why? Because x to the 0th power is just 1. So this term, even though it may not look like it has a variable there, it actually does. And it applies to the rules of a polynomial. Thus, we have a constant, but that constant actually is a polynomial. The first thing I'm going to do when solving these problems is look for either my horizontal or oblique asymptote. I need to get some water. So how do we figure out if this graph has a horizontal or oblique asymptote? We look at our degree on our leading term. So right here, our leading term is 120, and we have, it's a constant. And as I said, a constant is the same thing as saying x raised to the 0. And at the bottom, I have my variable, and this is raised to the first degree. It may not have it right there next to it, but that's actually where it is. And I created a little table, and I'm going to show you that table to basically break down what is my horizontal or oblique to see if it has an oblique asymptote. All right. So I'm going to look at the leading term, or the degree of the leading term. So this is at 0, and in the denominator of my leading term, it's at the first power. So if my degree on my numerator is less than my degree on my denominator, I'm going to have a horizontal asymptote at y equals 0. So that will be our first asymptote, and we'll also determine the behavior of this graph along with the vertical asymptote. So that's how we find our first asymptote. And as I said, start off with the horizontal because it can get you, prevent you from getting into a mistake later on when we get to removable discontinuities and such. So you start off with the horizontal asymptote, and that's where it is. Ours is at horizontal asymptote is at y equals 0. All right, now let's find our vertical asymptote. The second part is finding our vertical asymptote, and to do that is two parts. The first thing we're going to do is factor the numerator and denominator, and then we're going to check for any parts of the numerator and denominator that cancel out. Anything that doesn't cancel out, we're going to set it equal to 0. Doesn't cancel out in the denominator, we're going to set it equal to 0, and that will be equivalent to our vertical asymptote. So we had 120 divided by x minus 1. Luckily for us, yeah, that's perfect. We can leave that as is. And when I'm looking at this, I'm going to set my x minus 1 equal to 0. And so move over that 1, of course. And I'm left with x being 1. So we have a vertical asymptote at x equals 1. Now, there are, of course, instances where our numerator and denominator are both larger polynomials and they have terms that can cancel out. I'm not showing that in this video, but in another video I will. This one, though, is pretty straightforward. We just set since this is already factored, it's beautiful. We just set our denominator equal to 0, and that's what we get. This is our vertical asymptote. Can you have more than one vertical asymptote? Most definitely. Now, getting back to the question that was in the word problem at the top. How long can the drone fly with payloads of 2 pounds, 3 pounds, and 4 pounds? And what happens as the payload approaches 1 pound? So right here, so we have T being 2, or the payload being 2 pounds. 120 divided by 2 minus 1 equals 120. Then we have this, it would be 120 effectively divided by 3 minus 1, which is 120 divided by 2. We have 60. And then we have 120 divided by 4 minus 1, which is 3, which will give us 40. And each of these will be in seconds. So we have most of the behavior of this graph that we can actually draw a good portion of it. If this is our x-axis and this is y equals 0, this is our horizontal asymptote right here. And my graph will not cross this line, not to say that it can't cross that line. I like to think of horizontal asymptotes kind of like in Pirates of the Caribbean. They're pirate codes. Pirate codes are more guidelines rather than rules. Horizontal asymptotes are also the same. They're more guidelines versus rules. So the graph won't really cross this, but there are graphs that do cross the horizontal asymptote. And then we have our vertical one at x equals 1. So let me do x being 1 right here. Of course, I'm just eyeballing all of this, and I'm not going to cross this line. And I've done a couple of points. I know when x equals 2, y is equal to 120. So I know it's up here somewhere. We'll just do right there because I can. I know when x is 3, y is 60. So also that is up here. And on this side, when x is 4, oh, let me actually move that over just a little bit, Ted. When x is 4, y is 40. So my graph is decreasing. And this gives me the right-handed behavior of our graph. It will infinitely approach our vertical asymptote and also our horizontal asymptote. So this tells me the behavior of half of our graph. I can't just assume, though, that the other half will be right here or right here. I'm going to have to test points. And we could test points like 0. We could test points like -1. Doesn't matter. You can test whichever points you want. Now, I've already tested my points, and just for the sake of time and brevity, I already know that it ends up on this section over here. And this is our graph. As you see, once we have our asymptotes, it will largely constrain the behavior of our graph, or kind of like guide the behavior of our graph, which is why we started off finding our asymptotes. And then we can find a couple of points and graph from there. So whenever you're solving for a rational function, key things: find your horizontal asymptote first. They obey these kind of rules. You do that by comparing the degree of your leading term in the denominator and numerator. And following these rules, if the numerator is greater than the denominator, you won't have a horizontal asymptote, but there may be an oblique one, and I'll get to that later. If your denominator and numerator are of equal value, then we are equal degree, then we will use the leading coefficient for both the numerator and denominator, and that will tell us what y will be equal to, and we'll have a horizontal asymptote at that y equals value. And then if your numerator is less than your denominator's leading term, then we have a horizontal asymptote at y equals 0, which was the case for this graph. All right. That is the end of this graph. You can stay tuned for another one where I'll go into one where we will have either a oblique or a horizontal asymptote that is not at 0. Peace out.